Hi, my name is Sandra Korte-Kerzel. I'm the spokesperson of this CRC. It's called CRC1394. It's funded by the German Research Foundation, and the title is Structural and Chemical Atomic Complexity from Defect Phase Diagrams to Material Properties. I'm very happy to welcome you all here. We're lots of people in this talk, and what I'd like to do today is to give you an overview of our motivation for this collaborative research center and the scientific aims and the ideas behind this entire project. So as material scientists, we aim to develop new or better materials and processes, and we want to make them available for energy conversion, for safe mobility. They must have good recycling potentials, and generally we might want to achieve green manufacturing as well with them. We know what we need for this, and we actually teach the key ingredients. There are, for example, lattice defects that govern the elements of material properties. They are the effects of alloying on these defects and the properties and processes by which a material's microstructure actually evolves and is created at the end of the process. And we also teach and know how the phase composition and the stability is governed by the underlying thermodynamics. So in research, we use new experimental methods such as nanomechanics or high-resolution TEM to now also reveal much of this. But we see that there are much more complex configurations at the lattice defects, like in ordered crystals. And we also know from coupling our research with techniques like atom probe tomography that there is a local chemistry that's really interesting, and that goes beyond a level of, say, segregation or an increased average concentration. At defects like this, hang on, presentation is no longer working. There. We also know that such ordered structures, defect with an order in the structure and a chemistry, they are often found to be related with microstructural processes, like, for example, grain boundary mobility that you would need in recrystallization and grain growth. And we've now also started to do some important work that started several decades ago, in which we consider the stability and the structure of different defects and their chemistry. And we are now using high throughput computing and machine learning as essential tools, so we can actually set this on a much wider basis. So we're not just looking at the defects or trying to categorize them systematically, we're also trying to look at the chemistry and the stability. Now, that's quite exciting, but we think that there were also some insights that were missing, and that's the essential motivation for starting this CRC. We believe that there is a disconnect, and there's a disconnect between our existing fundamental concepts that you see on the left and the boundaries that we are currently pushing in research. And what we are missing in many cases are the direct physical links. For example, how a certain dislocation or a grain boundary with a given defect structure and chemistry is linked exactly to its mobility. And there's also no coherent framework to consider this, even if we figured it out. So, for example, why is a defect stability not considered directly with the phase stability? In a systematic, accessible manner that's not just isolated to one set of defects, for example, grain boundaries in a given material. And we need to be able to put all of these defects into competition to see which one is actually in the material, which one is the one that governs material properties. And we need to link this to the final ensemble of all properties, and they might be mechanical properties or they might also be corrosion. They are the two main properties that we are looking at in this CRC. So that's what we want to achieve over the next decades, and all of the starting points and ingredients that you see are already on this slide. Now, the natural starting point to structure our SFP, to structure our research, are the defects themselves, or rather the structural and chemical atomic complexity of defects. And what we want to do then is to describe and predict defects, and we want to do this in a coherent framework, the defect phase diagrams. And lastly, the whole point is to actually couple these mechanisms and properties at the defect scale and ultimately couple them to the resulting bulk properties that we need for engineering. And they might be mechanics or they might be corrosions, and they are the two that we'll consider here. And all of them together these three components, they will allow us to realize a new materials design toolbox. That will be for scientists and it'll be for engineers, and it'll allow us to advance our understanding. It'll provide a new platform and a large database to engineers, and hopefully give us a more powerful tool for materials design and materials selection. Because these three concepts are all absolutely essential to what we do in this CRC, and you will be dealing with these three topics an awful lot. And we also have novel concepts in there, like the structural chemical atomic complexity and the defect phase diagram. What we do now is we look at them very quickly, and there will be follow-up presentations to then give you a closer view into each of these topics. So what we're going to do here, let's start at the beginning with the atomic structure and the chemistry of defects. And what we understand by this is the structural and chemical atomic complexity is the complex arrangement of all atoms that form a defect, and that's in terms of their position and their elemental species. So let me give you a few examples of why we know that's important to consider this structural and chemical atomic complexity, and where we think we really have considerable gaps in our understanding today. So the first example I want to give you is the case of ductilisation of magnesium. What we want to do is want to realize its really full potential as a lightweight metal. And so far, we've been using unfavorable atoms that have been used, like yttrium or rare earths. And what we're aiming at is to get favorable properties while replacing these atoms. So we've been considering the stacking fault energies of alternative elements in combination with quantum mechanical calculations. And that's proven immensely successful, with a dramatic effect on ductility that we achieved with putting in aluminium and calcium, very commonly used elements, and by putting them in at a much lower content than we would normally do. So if we are honest with ourselves, that sounds great, but we still have questions in spite of being successful here. The stacking fault energy on the basal plane is an indicator of what's going on, but it's not actually a mechanism, particularly not for flow off the basal plane. Because the macroscopic deformability that we saw here and the calculated stacking fault energy, they must be related via some sort of nucleation and stability of non-basal C+A dislocations. And how these come about, that's determined at the local atomic scale, but we don't know it yet. The second example is structural and chemical complexities in intermetallics, in structural materials for extreme conditions. And it's not like you only get structural and particularly chemical atomic complexity at defects. It can be there in the crystal already. And we have binary and ternary ordered crystals where our understanding is really very limited. We don't even know the fundamental defects in these materials yet in a lot of them. For example, we don't know what a perfect dislocation in perfect stoichiometry looks like. So using nanomechanics, we are now able to, for the first time, measure critical stresses and image the underlying dislocation in high-resolution transmission electron microscopy. And we can connect this data with calculations of how the defects might work at the atomic scale, how dislocations might work, or how we shear a crystal. And you may expect to just transfer the concept of a simple dislocation glide on a densely packed plane, but if you look at this in more detail, then you actually see that it's not always that easy, and that simple shear might not always be favorable. And you see other mechanisms, like the synchroshear mechanism that you saw here, where the atoms actually make a more complex movement, but don't have to move quite as far away from each other. So in this case, again, we are now in a position to answer fundamental questions that we've been having with respect to ordered lattices. For example, which atomic configurations of defects actually appear? Which planes can such defects move on? And how does that affect the macroscopic properties of a complex crystal, or the interfaces that it forms when we look at a composite with a metal? Right, the third example is from corrosion. Taking a very common material here as an example, in precipitation hardened aluminium, we see a change in corrosion behavior when we conduct a heat treatment. For example, we see a change from a local attack to a more homogeneous attack at grain boundaries. And what we typically do then is we look more closely into the material, we look at microstructures, we look at the grain boundaries, and we find here that there is a segregation of copper that we find after hardening. But of course, there is potential to go deeper here as well. We know that grain boundaries containing alloying elements do not normally correspond to ideal geometries with elemental concentrations that we just look at sort of an average scale. But instead, what happens there is the atoms segregate and we actually form structures, complex structures at the atomic scale. So what we need to ask here is how these form the basics of, for example, microgalvanic elements, or how the local structure and chemistry might give us diffusion paths that we can understand better with a better knowledge of what the defects locally look at and how stable they are. So what we need to do is we need to really get a scale bridging understanding to design corrosion properties in the same way that we look at mechanical properties as well. So in all three cases, we are already really successful at connecting observations and models with material properties. But a lot of the time, it's a bit of hand waving, and the true physical link is actually not yet identified. But we think in most of these cases, we know where it is, where we are going to find it, and it's in the local atomic complexity of defects at the atomic scale. And we are also convinced that resolving the structure and chemistry of defects is then the key to give us the materials physics, the understanding of what's going on. And with recent developments in experiments and in modeling, we can now finally embark on this challenge and actually get to the bottom of the complexity at the atomic scale, and we can consider both structure and chemistry together. So, understanding of the atomic structure and chemistry of defects is our logical starting point then, and we hope it's the starting point for a new toolbox for materials design. In order to realize it and to apply it, we need to go a bit further. So, on the basis of the atomic complexity, we will be able to determine the stability of defects. And that's a very significant step, because it will allow us to transfer the powerful concept of bulk phase diagrams that each of you will know to the description of defects. And that in turn will allow us to create a comprehensive and material-independent new tool that will physically link the underlying defects with material properties. So that means we'll combine two strategies which are now generally employed next to each other. On the one hand, we have the manipulation of microstructural defects like dislocations and grain boundaries. And on the other hand, we know how to control the desired phases from phase diagram. So in the future, we'd like one new and integrated approach. So similar to phase diagrams in the bulk, we are now in a position where we can describe the thermodynamic stability not only of crystalline phases, but also of their lattice defects. And within this CRC, we'll therefore endeavor to actually expand the powerful concepts and bring the two together, and that will form something in unique structure in the form of defect phase diagrams. So a defect phase, in the term defect phase diagram, is a structurally and chemically distinct atomic scale defect configuration with a thermodynamic stability. So it's not just the defect and it's not just the stability, it's both of them together. And this is why we can use this definition to then formulate defect phase diagrams that we will want to link with properties, of course. Actually, we need to go much deeper into this idea, and it means that if we want to look at the distinct phase, then actually for every character of a defect and the equilibrium conditions, they depend on temperature and chemistry and have to be found, and you can see this here, for two different types of dislocation. And that may lead to a textbook dislocations in a solid solution, or at higher alloying content, you might actually form particular structures, you might form complex defect phases, like what you see on the bottom left here. Yeah? Quite far away from just the sign that you make, there'll be a local structure and chemistry that might form. And for this collaborative research center, we have now formulated a few key hypotheses which are centered around these defect phase diagrams. And these are that we think local defect phases exist, and they are controllable, and they are controllable by alloying and by thermomechanical treatments. So two things that we are doing already, and two things which are really technologically accessible. Our second hypothesis is that we can resolve, predict, and probe these defect phases, and that transitions between the defect phases will be important. And what they'll do is they'll induce property changes at the macroscopic scale. And that the defect phase diagrams we propose to develop will perform an equally important role as we have today for bulk phase diagrams. In the future, we'll use this kind of defect phase diagram to design materials with certain properties. Now, you can see we've already put quite a bit of thought into what a defect phase actually is and what the defect phase diagrams must be like, and they have some key properties. So in addition to requiring one defect diagram for each type, that's what I've already said, we can also see that they can't be defined on the same axes as we do for bulk phase diagram. For example, the bulk composition can't be the x-axis, but rather, as illustrated in the example, we need to look at the local composition. It'll be the chemical potential that we have in an axis, and we'll talk about this in a bit more detail. And we'll embed these in the framework with a direct link to the mechanisms and therefore also the properties of each defect. That's important because that's how we get from our defect phase diagrams to engineering properties. We need the defect phase, we need the mechanisms that are related to this phase, and then we get to engineering properties once we set all of these into competition. So that's a sort of intuitive view that we just had there. And what's important to notice is that really everything that we normally do is actually there. So we determine sample conditions, and that's something we do in our experimental space. There might be an experiment in the computer, or it might be an experiment that we do in real life. And so what we're going to look at there is we look at the structural and chemical atomic complexity, and we'll see how that's related to the actual properties that we get on the far right in the engineering space. What we first need to do is we need to look at the boundary conditions we have, look at the structure and chemistry of our defect, and then we translate this into mu space. That's our general space that's determined by the chemical potential. And by, for example, determining the chemistry and the temperature in our bulk sample, we can actually get to a point in every given experiment where we can compare all the data that we collect across this SFB. So this then allows us to construct and populate defect phase diagrams every time we have a sample for a given place in mu space and have a structure and a chemistry. We are populating the defect phase diagrams, and those in turn will be really intricately linked to the resulting mechanisms and properties that we'll look at by means of guided probing. And each of the projects that we have in this CRC might work in one or two or all of these areas and really help putting data into all of this. So with this, we'll have an integrated approach that starts from the atomic complexity of defects to describe them in defect diagrams, and that allows scale bridging, control of defects, and there's also tailoring of materials and their properties in application conditions that would be our engineering space. So this will importantly allow us also to combine different physical processes from their joint origin at the atomic scale, and for this we've chosen to consider mechanics and corrosion, and to consider them as concurrent processes. We believe that if we follow this vision, and we'll do this as a close-knit team, as a new team now, not just as PIs, but with all researchers that have and will join the CRC, and we have this with backgrounds from experiments and from theorists, then that we can do with materials physics, with mathematics. We can really pioneer a new paradigm in the description of defects for materials and to overcome the limits in materials design that we've had so far. We'll do this as a team, and so this means all CRC members, but we think this also means the greater scientific community, because everything we want to do, the frameworks, a lot of our data, we'll make open access so that the entire community can contribute and make this framework grow. So with this in mind, I'd like to introduce you to our 12-year horizon. A CRC can be funded for 3 times 4 years, so we have a 12-year horizon for which we've planned our research. In general, we'll follow our general aims to first form a firm foundation, then explore the newly developed concepts, and ultimately we want to employ predictive defect and materials design. Now, to enable the greatest possible synergies between the projects and all the computation and experiments we do, we've selected just 2 material systems. And we've done this on the basis of 4 criteria. They are that there is a documented relevance of the defects complexity and chemical atomic complexity in the material, that we get them in both solid solution and the intermetallic, that we know there is the existence of a good composite, that's a technologically advantageous composites of the solid solution and the intermetallic, and that we have technical relevance of the system. And in the 3rd funding period, we then use the identified mechanisms and structures for further materials selection and to generalize our findings. The materials intrinsic complexity will actually increase over the 3 funding periods. We'll start with the system magnesium with aluminium and calcium, a hexagonal system, at least in the intermetallic system. Then we'll have the additional crystal structure and magnetism that will be found in the 2nd model system, that's iron, niobium, aluminium. And across all 3 funding periods, we then anticipate to construct and populate the first defect phase diagrams and try and improve our strategy for doing that. And then finally complete this as a full framework by including fully kinetic and predictive modeling. On the way, we'll achieve substantial potential for transferring that knowledge already to the greater scientific community. And that will be in terms of methods for characterization, coupling of mechanisms, and finally the materials design toolbox, which will be available to the scientific and also the engineering community. Within the CRC, we'll focus on driving the fundamental knowledge and the underlying advances so that we'll have development of new magnesium and iron alloys from the 2 model systems. That will be directly dependent on our results. And we'll focus on the basic science in this CRC, but from the 2nd funding period, we'll anticipate having transfer projects that look at concrete alloy engineering, alloy manipulation. So we have an ambitious perspective and we want to realize this. And that's how we're going to organize ourselves. We are organizing ourselves into 3 project areas, A, B, and C, and they have been assigned according to the dimensionality of the defects that are in the focus of each project. It might not look exclusively at this defect, but the one that's in the focus. So for example, 1D would be dislocations and their associated stacking faults. The project area B would be 2D, and that's grain boundaries, phase boundaries, and also surfaces. And we'll be looking at metallic, intermetallic composites in area C, and also bridging all dimensionalities from point defects to the bulk phase in this project area. All of these scientific projects that are organized in these project areas, they'll be supported by an integrated research training group, short MGK, we'll have a service project that will perform material synthesis, and we'll also have dedicated developments for research data management. And I'd just like to give you a little bit more detail on our research group in a few more slides. So rather than introduce you to individual projects now, which you might look at later, I like to just highlight here the large synergies that we expect to have between the projects and also between the project areas. So first of all, we made it a point that all projects are concerned with the same material. We'll all be looking at magnesium, aluminium, calcium for the next 4 years. And we'll cover the entire spread between the solid solution of magnesium with aluminium and calcium and the intermetallics that form there. And we'll also go in the middle, we'll also look at the composites. So all the results, all the insight, all the material-specific methods, they can be shared directly between all projects. As a second thing, we also consider all scales, and we do that both in the experiment and in computations. So shown here, for example, it's just one example, is the case of dislocations in area A, and it's a 1D defect, and we'll measure properties of individual phases and their defects. We'll model their structure, the processes of motion, and relate both directly to experimental characterization at the atomic scale. Now, as a third thing, we'll aim to bring mechanics and corrosion together, and we do that based on their joint origin at the atomic scale of defects. And we therefore have on the same materials projects considering deformation and corrosion in great detail but separately, and how one influences the other and how they occur after each other. We'll then look at and we'll have a truly coupled considerations as our aim for the second funding period. Now, lastly, we developed research data management based on Pyron as a platform, and it'll enable us to bring together the data from all of these different methods. That means, hopefully, that amongst the projects we'll have early career researchers in each of the projects. There'll be a shared common interest as their work is performed on the same material, and they'll all be using complementary methods and studying concurrent mechanisms. And they'll also be able to store all the data in one shared database. So we hope that not only gives shared interests, but we think that's also a great basis to have a joint integrated training group that will be successful and really be complementary in terms of what we teach to make everyone understand each other, and to have all researchers in this SFB go away with really good skills and also insights into adjacent areas in terms of properties, methods, how to organize themselves and grow as researchers and also as a person. To support this, we'll also have training within our international networks. We have summer schools, there will be soft skill training, and of course, we also simply provide a platform for everyone to interact and participate in the CRC. Now, the starting team that thought up this CRC consisted of 20 PIs, and now it's our aim to really support and encourage early career researchers and diversity for everyone who joins this new team. And the first thing we do is we really consider our early career researchers as essential team members, as future PIs, future colleagues, and as developing researchers or professionals. And as a CRC, as a structure, we can really provide a uniquely supportive environment. That means in hiring, we'll hopefully continue and transfer the high participation of female PIs in the senior and tenure researchers level to our new team members. And we've set ourselves an aim of recruiting 35% female team members, and we try to attract them by acting as role models and through a flexible recruitment scheme also to hire early female candidates for every consecutive funding phase. We pledge to consider family-friendly scheduling of all CRC events, and we've done that in the preparation of this project already. And if you feel we can do better anywhere, or we have specific requirements in this, then please never hesitate to get in touch. And overall, we hope that in the future we can attract and also reflect diversity as best as we can as a group, as a visible group, as a collaborative research center. Now, our daily research environment is at RWTH Aachen University as the spokes university, and we have two contributing institutions. That's the Max Planck Institute for Eisenforschung in Düsseldorf and the Friedrich-Alexander University Erlangen-Nuremberg, of course. We also have a strong international and national network in which we plan to showcase and integrate this CRC, and we provide really good opportunities for networking to our PIs and also to our early career researchers. The PIs actually are already active, for example, in the German community that you can see here. Examples are the Materials Physics section of the German Physical Society, the German Society for Materials, or Corrosion as well. Now, that's the team of PIs that originally put together this proposal, the new concepts that have been assembled from different disciplines. And there are different disciplines like corrosion science, materials science, mathematics, mechanical engineering, and physics, and they'll all be important to this project. And they also, all the PIs bring together the experimental and computational methods that we need. And we'll teach everyone what they need to know to work in this project, and hopefully everyone will go away knowing a lot more about these and do an awful lot of exciting science with this. We all consider ourselves really lucky to be in a group like this, and we not only bring together absolute experts and specialists in these areas, but it's also so far always been an awesome group of colleagues who really like working together. And I think we'll keep doing this for the next 4 or hopefully 12 years. Now, we hope to grow into a group with more researchers, with more members of the CRC, and we also hope to take this vision out to the scientific community. So we've known for a long time that defects determine many important material properties. But it's now that we can actually capture their full complexity, and we can do it experimentally and computationally. And the first work in this direction has shown us that really nature is, of course, much more complex than what we teach and than what is part of our textbook knowledge. The aim of this CRC is to create a new and a quantitative description of the local structure, chemistry, and thermodynamics of defects that govern macroscopic material properties and that allow us to establish a direct link between the mechanics and corrosions in materials design. We believe that this will lead to a paradigm change in the description of metallic materials, and we want to be the pioneers that bring across this paradigm change by creating a new and a powerful new materials design box.